In 13.2, we're going to continue our discussion on probability by discussing complements and unions of events. So we're going to start that off with an example. So suppose there are 529 people in a room, and we want to know how many people graduated from college with an associate's degree. How might we go about this? Well, let's assume that those people are people from the PCC graduation. Say we're at the graduation, and there's a lot of people in the room, and we want to figure out how many people graduated with an associate's degree. Well, probably most of them did because they graduated that day, right? So an easier way to count might be to see how many people didn't graduate and then just subtract that number from the bigger number. So say like 20 people didn't graduate, then there would be 509 people who did graduate with an associate's degree. So that's called the complement. Now recall that the total probability available in a sample space is 1, as it goes from 0 to 1. If we want to know the probability of an event happening, it might be easier to figure out what the probability of the complement of E happening is and subtract it from 1. So the complement is everything else. It's like the opposite of it. Now, we remember that from set theory. So if we wanted to compute the probability of the complement, if we considered E to be some event, then the probability of E complement would be 1 minus P of E. It's just the opposite of it. So for example, say we roll a pair of dice. What's the probability of rolling a total that is less than 11? Well, the highest number we could roll on a pair of dice would be a 6 and a 6, which would be a 12. So less than 11 would actually be pretty big. So let's think about E as being the probability of rolling less. So let's let E be the probability of rolling less than 11. So probability of rolling less than 11. And then E complement would be the opposite. So the opposite of rolling less than 11 would be the probability of rolling greater than or equal to 11. Because that would be less numbers to count. So greater than or equal to 11. So if we think about it, how many ways can we roll an 11? 11 would be greater than or equal to 11. We could roll a 5 and a 6. And then a 6 and a 5. That would be equal to 11. That's the only two ways you could do that. And then the only other way to get greater than or equal to 11 would be a 12, which the only way to do that would be a 6 and a 6. So if you think about it that way, the number of ways to roll 2 die is 36. You recall that because it's 6 times 6 die, 6 times 6 numbers on each die. So the probability of rolling greater than or equal to 11 would be 3, because there's 3 ways out of 36. So if we want to think about the probability of E, it's the exact opposite. So since the probability of rolling greater than or equal to 11 is 3 out of 36, the probability of rolling less than 11, which is what we're looking for, is 1 minus 3 out of 36, which is going to be 33 out of 36. And we can reduce that, and that would be 11/12. So that's looking at it the opposite way. I mean, you could have totally figured out this by figuring out how many ways there are rolling less than 11 and listing all those out, but it's a lot easier just to write the opposite of it, which is just these. Alright, so now unions of events. Again, this comes back from set theory. Often we want to know the probability of more than one event happening at a time, and we do this by figuring out the probability that the separate events will happen and take away the probability that both events will happen. So here we use ideas of unions that we learned in set theory. So recall the symbol for union was the U-looking symbol. Looks like this. And if you think about union, I'm going to draw a picture again. So if we have two events, we'll look at them like Venn diagrams, E and F. The union is all of this together. So union is all of the two circles here if we had E and F. So we want to figure out the union of them, of this or this happening. Then you'd have to take the middle out because you would actually count it twice. So the probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. Because in the picture here you can see that we're actually counting this intersection, that piece in the middle, twice. So we have to take one of them out so that we don't overcount. And if E and F have no outcomes in common, they are called mutually exclusive. Mutually exclusive events. And in this case, since E intersect F would be the empty, so since probability of E intersect F would be 0, then the formula would just simplify down to E union F equals probability of E plus probability of F. There's really no reason to memorize two separate equations here. It's just that if they have nothing in common, then you subtract nothing. Alright, so let's look at some examples here. So say we select a single card from a 52 card deck. What's probability of drawing either a club or an even card? Alright, so if we think about this, a club, how many clubs are there in a deck? There are 4 suits, and clubs make up a fourth of them, so there are 52 divided by 4 clubs, which is 13. Now, if you're not familiar with deck of cards, make sure you get one, or you have to pull up a picture on the internet to see the decks of cards. So the probability of drawing a club is 13 out of 52. Probability of drawing an even card. So even cards, we have a 2, a 4, a 6, an 8, and a 10 in each suit that are even. There's no 12. And then there's 4 suits. So we got 1, 2, 3, 4, 5 cards and 4 suits. So that gives me 20 even cards. So the probability of drawing an even card is 20 out of 52. Now the probability of drawing an even club card, so that would be the intersection of cards that are clubs and even, would actually be 5, because there's 5. These 5 are also clubs, so we've actually counted those twice. So that's 5 out of 52. So we put those together, we get 13 out of 52, plus 20 out of 52, minus 5 out of 52, which is going to equal 28 out of 52, which is going to give us 14 out of 26, which will give us 7 out of 13. And we can turn that to a decimal too, but I can leave it like that as well. Alright, so let's take one more example like this. So it's probably that we draw a diamond or a face card. That word or is really important. Whenever you think about unions, you'd have that word or in there. So the probability of a diamond, let's see, so diamond's the same probability as a club. There's 13 of them. There's 13 of each suit. Probability of a face card, okay, so for a face card we got queen, king, and jack in each suit. And that's 4 suits, so there's 12 face cards. Again, pull you out a deck of cards if you don't know the count here. And the probability that we have a face diamond card, well, in each of those faces there are 3 diamonds. There's a diamond of a king of diamonds, queen, and jacks, so we have to subtract out those 3. So the probability is going to end up being 13 out of 52 plus 12 out of 52 minus 3 out of 52. And that's going to equal 22 out of 52, and this one I'll turn to a decimal. That's approximately 0.42. It's about 42% of drawing a diamond or a face card. Okay. If you're giving any of the 3 of the 4 quantities in the formula, you can use algebra to solve for the other. So suppose, for example, I'm given that the probability of A is 0.35, probability of A intersect B is 0.15, probability of A union B is 0.65, and I want to find the probability of B. So first I'm going to write the formula out again. So I have probability of A union B is probability of A plus probability of B minus probability of A union B. Alright, so I want to fill in if I know any of these things. So do I know the probability of A union B? Yeah, that's 0.15. So I'm going to replace this to 0.15. Probability of A is 0.35. Probability of B I don't know, so I'm going to give it a variable. I'll just call it X. And probability of A union B is 0.65. Oops, sorry. I got those backwards. Sorry, I do have those backwards. Let me change that real quick. These two are backwards. Probability of A union B is 0.65. And probability of A intersect B is 0.15. Sorry about that. Alright, so if I try to solve that, well, first I can combine these two terms on this side. So that's going to be 0.65 equal to 0.35 minus 0.15 is 0.2 plus x. And then just subtract 0.2 from both sides, which will give me 0.45 equals x. Or also, since x is p of b, I say p of b equals 0.45. Alright, now let's look at a chart of things and see if you can tie this together. So the following table here shows the amount of time consumers spend shopping on the internet per month with their annual income. So what we're doing is comparing the amount of hours people spend shopping on the internet with their annual income. And here on the bottom and on the right, we see totals for each of those. Alright, so what is the probability the consumer we select either spends 0 to 2 hours per month shopping on the internet or has an annual income above $40,000? Alright, so they spend 0 to 2 hours per month on the internet. So how many people spend 0 to 2 hours per month on the internet? Well, we can let that be E. We'll let that 0 to 2 hours per month be E. We'll let F be has an annual income below $40,000. And then E intersect F is both of those things. So the probability of E is going to be equal to 544 out of 1,600, because that's how many people shop 0 to 2 hours on the internet. And the probability that they make below 40,000 is this number, which is 592 over 1,600. Alright, now I want to see if they have anything in common. Well, are there any people that make below 40,000 and shop 0 to 2 hours on the internet? Yeah, we got these guys, because actually we counted that person here, and we've also put them in this count, so we've overcounted them twice, so we're going to have to subtract that 272 out of the number. So if we put these together, we get 544 plus 592 minus 272. And that equals 864, and all of those are over 1,600, because that was the total of all the people. And that equals about 0.54, everything in a decimal. All right, now the next question says, which probably a consumer that we select randomly either spends 10 or more hours on the internet or has an annual income between 40 and 60,000. Okay, so let's look at the 10 or more hours on the internet shopping. That's a lot of hours. All right, so 10 or more hours is going to be that 480 there. All right, so that's 480. I'm going to skip some steps here. That's 480 plus income between 40 and 60,000. So income between 40 and 60,000 is here, so it's 512. And then we want to see if there's any overlap. So are there any people that spend 10 or more hours on the internet and earn between 40 and 60,000? Sure there is. So 10 or more hours on the internet between 40 and 60,000 would be this number right here. So we're going to subtract out that 160. And if we do that, you get 832 out of 1,600, which equals 0.52. Alright, so that's all I have for section 13.2. If you have any questions, please let me know, especially on the homework.